All right, we're going to start with a quick warm-up. So I'll put the warm-up up here, and then you can try it on your own, and we'll pause the video while you do that, and then I'll reveal the solution. So warm-up is to find all local extrema of the function y equals x times the natural log of x. All right, pause the video, and then I'll reveal my solution. All right, here's the first part of the solution. We need to find a derivative first. So in order to do so, we need to use the product rule. dy dx is equal to the first function x times the derivative of ln x, which is 1 over x, plus ln x times the derivative of x, which is 1. Simplify that and you have 1 plus ln x. Now our critical numbers are where that derivative is equal to 0 or undefined, so it's not going to be undefined, so we can set it equal to 0, and we find out that x is equal to 1 over e. Now the next step is for us to analyze the sine of y prime. So let's use some test values. 1 over e is around 1/3, so we can certainly test for instance, the number x equals 1. If we test x equals 1 in the derivative, we get dy dx is equal to 1 plus ln of 1. ln of 1 is 0, so that's going to give us 1 plus 0, or 1, which is a positive number. And then the value of the natural log changes signs at its 0, so we're going to be negative to the left. Now, of course, if I want to be really correct about this, the domain of this original expression, whoa, that was bad. The domain of this original expression is x is greater than 0, since the domain of a natural log function is x is greater than 0. So what does this mean? We just found that y is decreasing to the left of 1 over e and increasing to the right of 1 over e. That means we have a low point at x equals 1 over e. And so 1 over e is the x value at which the local minimum occurs. We need to now find the y value. In order to do that, we need to go back to the original function. So the y value is 1 over e times the natural log of 1 over e. The natural log of 1 over e is negative 1, so that means that our y value is negative 1 over e, and that is the local minimum value of y equals x ln x, and it occurs at x equals 1 over e. So that's our entire solution. All right, now we're going to move on to our notes for the day. And this is a continuation of the video notes for 5.2. What we're doing in 5.2 is we're looking at integrations that give us a result that's equal to a natural log. So let's start with this one. The antiderivative of 3x over x squared plus 5 with respect to x. This is going to call for a U-substitution. So let's let u equal something whose derivative is conveniently laying around nearby somewhere in the integrand. So u is equal to x squared plus 5, and then du is equal to 2x dx. Now what we can do with this integral is we can rewrite it. I'm going to pop that 3, the constant multiple, out in front of the integral. And then I'm going to rewrite this as 1 over x squared plus 5 times x times dx. Now I don't have that 2x dx, but I do have the x dx. So 1/2 times du is equal to the x times dx. right? If we take that equation above and solve it for x times dx. So that means that this x times dx can be replaced with 1/2 times a du. The 1 over x squared plus 5 is a 1 over u, and then I still have that constant multiple out in the front. Okay, 3/2 can just come to the front. The antiderivative of 1 over u is the natural log of the absolute value of u plus c. And now we can replace the u with x squared plus 5. Now, x squared plus 5 is a quantity that is always positive, so you'll notice answers that don't have absolute values around them because they're not necessary. In fully simplified form, this is just 3/2 times the natural log of x squared plus 5 plus c, because the absolute value is not necessary around a quantity that's always positive. All right, let's move on to another example. In example 2, we have the antiderivative of secant squared of x over the tangent of x with respect to x. So again, for a substitution, we're looking for a quantity whose derivative is conveniently laying around nearby in the integral. So we can let u equal tangent of x, and our du is secant squared of x dx. Wasn't that really convenient? All right, so when we rewrite this, we have 1 over the tangent of x times the secant squared of x dx. That means we have a perfect 1 over u du. So this is the natural log of the absolute value of u plus c, replacing u with tangent of x. This is our final answer. Absolute values are necessary for this answer because the tangent of x can either be negative or positive, so the absolute values are really necessary to ensure maximal domain in our answer. All right, let's take a look at example 3. Here we have the antiderivative of x squared minus 1 over x. What we'll need to look out for here is that we have a single term in the denominator. If we have a single term in the denominator, that means that I can just divide through. So if you see a single term in the denominator, just go ahead and distribute the division. What that means is we'll rewrite this as x squared over x minus 1 over x. Now we can do this term by term. Let's simplify first though. X minus 1 over x. The antiderivative of x is 1/2 x squared, and the antiderivative of 1 over x is the natural log of the absolute value of x. And we have to add on our plus c. All right, let's check out another example. In example 4, we have the antiderivative of 4t over t squared plus 6 with respect to t. You'll notice that we have a square in the denominator and t raised to the 1 power in the numerator, so that means that we have a function and its derivative more or less. So we can let u equal t squared plus 6. du is equal to 2 times t dt. Now if you want, one of the things that you can do is you can take that 4 and you can split it up into 2 times 2t dt. So that's our numerator. and then 1 over t squared plus 6. You might not necessarily write all these steps, but these are part of the thought process here. So we have the 2, 1 over u, and 2t dt is du. So that gives us 2 times the natural log of the absolute value of u plus c. What are we taking the natural log of? T squared plus 6, and t squared plus 6 is an expression that's always positive, so the absolute values are not necessary around that one. All right, let's check out example 5. In example 5, we have an integral of 5 over 2x plus 1 raised to the 5th power. Now, in this case, we have a denominator that's raised to a power. This generally indicates that we're not going to have a result that's going to give us a natural log. So we can go through our U-substitution. U is equal to 2x plus 1, since 2x plus 1 is an inside function. Du is equal to the derivative of 2x times dx. And so we don't have a 2 times dx, we just have a dx. Dx is equal to 1/2 times du, just solving that equation above for dx. So that means that when we rewrite this integral, we can bring that 5 to the outside. We have 1 over 2x plus 1 to the 5th dx, and the 5 gets, the 2x plus 1 gets replaced with a u, and the dx gets replaced with a 1/2 times du. Let's bring all of our constants to the outside, and at the same time, let's recognize that this is not going to be a natural log, because the natural log is the result of a division of an antiderivative of 1 over x, which is the same as the antiderivative of x to the negative 1. This is actually u to the negative 5th power. So when we antidifferentiate, you can use the power rule on this. So 5/2 times, and the antiderivative would be u to the negative 4 divided by negative 4 plus c. So now let's do a little simplifying. We have negative 5 over 8 u to the 4th plus c is equal to negative 5 over 8 times 2x plus 1 raised to the 4th plus c. All right, so beware of those where you have a denominator raised to a power, because that's really not going to give you a natural log result. Natural logs are restricted to 1 over a variable quantity 2 of the 1st power, or rather that variable quantity to the negative 1 power. All right, in example 6, we have 2 times the cosine of t over 1 minus the sine of t, and we're taking its antiderivative with respect to t. So what we're looking for again here is a function pair where one function has its derivative conveniently laying around nearby. Well, we do know that the derivative of cosine is negative sine, but we're looking for a derivative that's going to multiply times the dt rather than divide it. So we can let u equal this entire denominator, 1 minus sine of t, and then du is equal to the derivative of negative sine, which is negative cosine of t, dt. And if we're rearranging things, we can bring that 2 to the outside, rewrite this as 1 over 1 minus sine of t, and then move the cosine of t outside of the fraction so that it's multiplying the dt. So what's cosine of t times dt worth? If we take this equation over here and we divide both sides by -1, we get negative du is equal to cosine of t dt. So this means we have 2 times 1 over u times negative du. Let's bring that negative to the outside, and then the antiderivative of 1 over u is the natural log of the absolute value of u plus c. Back substituting, 2 times the natural log of the absolute value of 1 minus sine of t plus c. All right, let's check out example 7. Here we've got the antiderivative of the quantity natural log of x raised to the third power over x with respect to x. Now, it might be a little bit more obvious to do if we separate things. So rewriting this integral, what we really have is, if we move that natural log of x outside of the fraction, we would have the natural log of x raised to the third power times 1 over x dx. Now it might be a little bit more obvious what our function and its derivative that's conveniently laying around nearby are. U is equal to the natural log of x, the inside function, and du is equal to 1 over x times dx. So right here, that 1 over x times dx becomes a du. So we have we have u to the third du that we're integrating, and that'll give us 1/4 u to the fourth plus c, or 1/4 times the natural log of x raised to the fourth plus c. Now let's try another one that's sort of similar. In this example 8, we have the antiderivative of 1 over x times ln x with respect to x. Again, this is another one where we might want to sort of separate things out. So rewriting, this is 1 over ln x times 1 over x dx. We can see where this is going. U is equal to ln x, and du is equal to 1 over x dx, because 1 over x is the derivative of ln x. So this just becomes a 1 over u du. The antiderivative of 1 over u is the natural log of the absolute value of u plus c. And then we just need to replace u with the natural log of x. All right, we're going to do one more quick one, and this one will be a definite integral. So in a definite integral, when we change our variable, we're also going to change our limits of integration. So the integral from 1 to 4 of 2 over 3x plus 1, we can let u equal 3x plus 1, and du is 3 times dx. So sort of separating things out here, we have, let's bring that 2 from the numerator as a constant multiple so we can bring it outside of the integrand. Integral from 1 to 4 of 1 over 3x plus 1 dx. So let's attack that dx first. What is that dx worth? If we take our equation over here and we isolate the dx is worth 1/3 of a du. So we have 1/3 of a du. The 1 over 3x plus 1 is a 1 over u. And I'll bring down the 2 on the outside. Now what we have to be really careful about is what goes here and here on the integral. Those are assumed now to be x values. I'm sorry, to be u values. So the originals were x values. So if x is equal to 1, then u is equal to 3 times 1 plus 1, which is 4. So we're going to put a 4 here in the lower limit of integration that corresponds to x equals 1. If x is equal to 4, then u is equal to 3 times 4 plus 1, which is 13. So I'm going to put a 13 in the upper limit of integration to correspond to the x equals 4. All right, let's bring all of our constants to the outside. So there's a 2 times a 1/3, which is 2/3. Integral from 4 to 13 of 1 over u du. So the antiderivative here is the natural log of the absolute value of u. We don't need a plus c for a definite integral. That's from 4 to 13. Continuing, that's 2/3 times the natural log of 13 minus the natural log of 4. Now, it's perfectly fine to leave your answer in this way, but we also need to be prepared to rewrite our answer so that it can match an answer in a multiple choice situation. So you'll remember that a property of logs is if you subtract the logs, you can rewrite this as a single log of the division 13/4. So that's another possible answer. You'll see answers given in the back of the book where they've done this and changed the form of the answer, so you just need to be prepared for that. All right, that is pretty much it for the lesson.